So this next set of modules is going to be about how the concentration of a reactant changes over time in a chemical reaction. Okay, and now I'm going to do this new set of modules which focuses on how exactly the concentration of reactants and products changes with time. Like, what is the exact dependence of that concentration on time? And so you might want to know, well, why do I care about this? Why is this important? So I thought I would give you a few examples of why this might be important. One of them would be like for example, and for me, about 10 years ago, I had to have my thyroid removed because I had thyroid cancer. And so after they take out your thyroid, they treat you with radioactive iodine, which kills off any tiny little cells that might have remained. And so the iodine 131, which is in your body, which is, giving off radiation to kill these cancer cells, what you'd like to know is, well, when is it going to be safe for me to, be with my child or sleep in the bed with my husband? One day I brought home a Geiger counter from the lab and put it next to me in the bed, and it was going, and Steve said, yeah, maybe I should sleep in the other room for another night, So anyway, but when can you actually be sure that there was no longer a harmful level of that iodine 131? Another thing you might want to know is if there was a toxin that was introduced in drinking water, how long before that toxin gets down to a safe level? That's something that you'd really like to know. How long, well, anyway, so that would be a much more complex kind of situation because the toxin could do many different things in the water, and there are probably many different rate processes that could cause that toxin level to go down. But the radioactive decay one is really simple because radioactive decay is what we call first order. You know about first order from what I covered earlier. And so we're going to be able to, in this course, very, an introductory type of course, we're only going to talk about how concentration changes with time when the reaction is first order. We're not going to be able to do anything more complicated than that. Okay, so what I'm going to do is go over to OneNote. All right, so here I am in OneNote. And so what I'm going to be doing, get some lines here, is I'm going to be talking about, for first order reactions only, how does concentration change with time? And I'm really going to be talking about the concentration of the reactant. I say the reactant because if you remember, this is what first order is. The rate law for a first order reaction is that the rate is simply proportional to the concentration of reactant. So it's really like you have A, the reactant A, going and forming products. Okay? So that's what we're going to be looking at here. So only first order. So this is first order, because this is the 1 power, okay? So anyway, what I want to talk about is how you will go from reaction rate to concentration changes over time. So in other words, how will we be able to use K and the time elapsed or the time passed to calculate the change in concentration. So before I start talking about reaction rates, I thought I would do kind of an analogy. Okay, and the analogy that I'm going to work with is, well, first of all, a rate is like a speed, right? You could say the rate that your car is moving, or you could say the speed that your car is moving. So a reaction rate is equal to the change in concentration divided by the elapsed time. We talked about that. If we're talking about speed, like the speed that a car is moving or the speed that you're walking, that's like this change in distance. Oops, I don't know how to spell again. Over the change in time. So reaction rate and speed are both changes in something over the change in time. Okay, so the question is, let's think about in terms of the car and the speed. Okay, so if you know the speed and you know the time that passed, so if you know how fast the car is going, can you calculate the distance that's traveled? Can you find the distance traveled? Okay, so how would you do that if you could? So I would say, yes, you can do this. Okay, that's easy if the speed is constant. So this is easy if the speed is constant. Okay, so how would you do it if the speed was constant? Well, speed equals distance over the change in time. Okay, so if you take the speed and you multiply it by the change in time, you'll get the distance traveled. So in other words, if you're going at 60 miles an hour and you multiply that by 2 hours, not worrying about sig figs here, that's going to be 120 miles, right? You can even use dimensional analysis there. Okay, so can you do the same thing or a similar thing for reaction rates? In other words, can you take, since the rate is the change in concentration over time, right? Can you take the rate and multiply by the change in time to get the change in concentration? Can you do this? What's the answer to that question? All right, so think about it. The reason you can't do this, I would say no, you can't. And I hope that you can guess the answer. The reason is because chemical reaction rates are never constant. You can't do this. The rate of a reaction is never constant. Why is it never constant? Well, because the rate always depends on the concentration of reactant, and the concentration of reactant is always changing as that reactant gets used up. Okay, so if you remember back from the very first day where we talked about a graph of concentration of reactants with time, remember it looks kind of like this. Okay, so at the beginning, you have a very big slope. Like you have a large change in concentration over change in time. So this is a large slope. So the slope, remember, is the rate of reaction. And here, now you have a very small change in concentration with time, which is the slope. So you have a smaller rate. So as remember, I said that reactions start fast and they end slow. Okay. So we can't use this idea that you can just multiply the change in time by the concentration, because if you rearrange this equation, multiply the change in time by the rate to get the change in concentration. You can't do this because this is not constant. And that's a big pain, all right? So we really can't use that simple method. So what are we going to do? There's a problem, okay? So in order to come up with an equation, so what we really want here is an equation that relates concentration of reactants. And in this case, like I said, we're doing first order, so there is really only one reactant. Relates concentration of reactant to time. So this is what we want, an equation that relates concentration of reactant to time. But the thing is that in order to get this, we need to use calculus. And I know that some of you have had calculus or maybe taken calculus now. But I want to tell you what calculus was invented for. So calculus is a branch of mathematics that was actually literally invented to handle rates that change with time. So it was invented to handle, in a way, rates that change over time. And chemical reactions definitely have rates that change over time. They start fast and they end up slow. Okay, so for simple reactions, so in other words, simple rate laws. So for example, that's what I really mean was for simple rate laws. For example, if the rate, like I said, for first order is like that, that's first order. Or it could work for a second order if it looks like this, proportional to the square of reactants, that's second order in A. Okay, so for these simple reactions, calculus allows us to get an equation like this. That means an equation that relates concentration to time. Okay. Yeah. All right. Great. So how do we do this? So what I'm going to do is show you how to do this. All right. So now obviously I know that many of you have never taken calculus and never will take calculus. But if we have a reaction A to products, and we know that the rate is first order, so this would be the negative of the change in concentration of A to the change in time, and this is the rate of change of A with time is proportional to the concentration of A to the 1 power. Okay, so that's first order. Then we can use calculus to solve this equation now. So I'm going to solve the equation using calculus, and those of you who understand some calculus, that's great. If you don't, that's fine. We're just going to get to the equation, and then I'm going to show you how to use that equation. If you know some calculus, listen up. If not, you can skip down to where I actually get the equation. All right, so in calculus terms, we need to take these deltas here. All right, these deltas are finite differences, and we need to make them infinitesimal. So this delta A over delta T is going to become the derivative, the change in the concentration of reactant A with time. And this is really like, it's an instantaneous slope. Okay, so instead of just having, taking a finite thing, delta A, dividing it by delta T to get a slope, you're really taking the slope at a point, which is really like a tangent line to the curve. Okay, and the curve I'm talking about is, the change in reactant with time, which has this thing. So the derivative is the slope at any point. I don't know why I'm telling you all this, because you don't have to know it, but it's all these different slopes as the reaction goes along. So dA dt is equal to Ka. And believe me that when I say that this is about the easiest equation that you could solve using calculus. So the first thing you're going to do is going to put the concentration of A on the left side, and this dt is going to go on the right. So we're going to kind of use algebra to make this minus dA over concentration of A equals K dt. And then actually I'm going to take this negative sign and move it over to the other side. Okay. So now what we're going to do, if you know calculus, is we're going to integrate both sides of this equation. And the integral of dx over x is equal to the natural log of x. So that's something that you learn when you figure out in calculus. So this is going to be the natural log of the concentration of A. And the integral of minus k dt becomes minus k, the integral of dt. So it's going to be minus k times the time, because the integral of dt is equal to t, but I have to add a constant because we only know what the integration of that is in terms within a constant. So I'm going to call the constant just constant, okay? And so we almost have an equation here, except we have to know what is this constant. We don't know what that is yet. Okay, so we want to know what this constant is, and I made a little mistake, so I erased a few things. So what we do know is that when the time is 0, the concentration of A is equal to the initial concentration. Okay. Okay, so we know that when the time is equal to 0, the concentration of A is equal to the initial concentration. So that means I can plug in a 0 here for the time. I'm going to do that. And I also know that the log of A when the time is equal to 0 is equal to A0. So this becomes A0. Okay, but of course k times 0 is 0. So what this tells us is that the constant is equal to the log of A0. So I can substitute that back into the equation over here, and I end up with the log of A is the log of the initial concentration of A minus k times t. So that means I can put in any time I want. I can multiply it by the rate constant k. I can subtract that from the natural log of the initial concentration of A, and I will get the natural log of A. Now, we're going to practice using this equation, so don't get all scared about it, okay? So that's why I'm going to use activity 6 for. So here we have a reaction. A goes to products, and it's giving you what the initial concentration of A is. It's 0.6 molar. And it's telling you that the rate constant is 0.0320 inverse seconds. And I actually never went over the units of a first order rate constant. So I may as well do that just to show you. So if you have that the rate is equal to Ka to the 1, a rate is always a molarity per second. It's a change in concentration over time. So the concentration units we use is molarity. So that means that we can use that to figure out what the units of a first order rate constant would be. Here we have molarity. A is in molarity units. So we basically can divide both sides by molarity, and we get 1 over seconds as the unit of K. So K, when it's for first order reaction, has units of seconds to the -1, or 1 over seconds, or s minus 1. Okay, so that's why we have that unit there for K. So here you're given the initial concentration of A, you're given the rate constant. And so the question that's asked is, what is the concentration of that reactant named A after 10 seconds? So that's what we're going to work on. So how are you going to work on this? Okay, so we're going to use the equation that we just got, that the natural log of A is the natural log of A0 minus KT. Okay, and so what you're going to do, first of all, I'd like you to take your calculator and find the natural log of A0, okay, which is 0.6. So you need to find this, get this number on your calculator. And most calculators, you'll actually have a button that says ln, okay? And on most calculators, you'll just put this number in and then put the 0.6 in parentheses, or I don't even think you need parentheses, and you should be able to get that value. So I want to just make sure now, as you're following along with this, that you do this on your calculator and you find the natural log of 0.6 and you make sure that this is the number that you get. So you should be getting this number right here. All right. So now you all know you can take the K, you know how to multiply. We know that T is 10 seconds, so we're going to take 0.0320 seconds minus 1, right? This is the K. And then we have 10.0 seconds. That's the T. So we're looking for what is the concentration of A at 10 seconds after the reaction starts. So we're going to multiply these two numbers together, and that gives you 0.320. But the equation, notice, has a negative sign there, so we're going to take the negative of that. So we're going to take, since it's ln A0 minus KT, we're going to put in the negative 0.511. This is the log of A0 minus KT. So it's minus 0.511 minus 0.320. So if you combine these two numbers together, two negative numbers, we get negative 0.831. Okay, so what is this number? Okay, this negative 0.831, well, if we go back and look at the equation, that's the log of the concentration after the 10 seconds have passed. So that's the log of A, right, at T equals 10 seconds, minus 0.831. Now, obviously, this number is negative, okay? So it can't itself be the concentration of reactant, because it doesn't make any sense at all for a reactant to have a negative concentration. So how do I solve this equation to get the concentration of A instead of the natural log of A? So this is where I have to use the fact that the natural log and the E function are inverse functions. So I have to take E to the natural log of A. That gives me the concentration of A, right? So that is E to the minus 0.831, okay? So in order to get the concentration, I need to take E to the number I get here, or, so on your calculator, you might have an E to the X button that you'll use, or you might have an inverse natural log. So what you're really trying to do is this. Inverse natural log of 0.831, or E to the minus 0.831. That's, put that in and see if you can get this answer. Okay, so the answer, which is the concentration of A at T equals 10 seconds, is 0.436 molar. Okay, so you can see that it is less than the initial. So if it's not less than the initial, then you did something wrong. So you have to make sure that you know how to do that. Okay, so the next question is, how much did the concentration of A change in that 10-second time interval? So we started with 0.6 molar, and at 10 seconds, the concentration, so this was the initial. At 10 seconds, the concentration of A was 0.436 molar, so we just subtract. And it ends up with 0.164 molar is the change in the concentration of A in 10 seconds. Okay, so now let's do it again, okay, because practice makes perfect. Okay, so we're going to use the same equation. The log of A is the log of A naught minus KT, but now we're going to put in 20 seconds here. And we have the same rate constant. Okay, so we're going to multiply this together, and we get negative 0.642. Meanwhile, we have the same value as we had before for the log of A0, minus 0.511. And this is minus KT, so we have minus 0.511 minus 0.642. If you add that up, you get negative 1.153. Okay, so that is the log of A at t equals 20 seconds. Now, in order to find out what is the concentration of A, well, again, we either have to take inverse ln minus 1.153, otherwise known as e to the x. So we're really taking e to the minus 1.153, okay? And we should get the same number. That should come out to 0.316 molar. Okay, and how did the concentration change from 10 to 20 seconds? If we go back and we look at what we had after 10 seconds, it was 0.436. Oh, you know what? This shouldn't have a 0 here. That's absolutely wrong. Okay, so we had 0.436 at 10 seconds, and now here we have 0.316 at 20 seconds. If we take the difference there, we get 0.120 molar. Okay, so let's take a look at that. So for the first 10 seconds, the change in the concentration for that first 10 seconds was 0.164. The change in the concentration for the next 10 seconds is 0.120. So what's happening to the reaction? You know, it's the same length of time that passed, but we have a smaller amount of reactant that reacted in that time. So this indicates that the reaction is slowing down, which we know happens over the course of a reaction. But our nice equation that we got from calculus accounts for all of that. Okay, so what's the concentration of A after 30 seconds? If the initial concentration of A is 0.6 molar, so remember that from before. So this is ln of 0.6 molar, which we figured out is minus 0.511 minus 0.0320, now times 30 seconds, okay? So if you multiply out that, you get 0.960. So now you're basically adding these two negative numbers. You get minus 1.471. So this is the natural log of the concentration that we want. So we will have to take the inverse natural log of negative 1.471 or e to the minus 1.471. Either way, you're going to get 0.230 molar as the answer. So if we want to know how much the concentration of A changed between 20 and 30 seconds, it went from 0.316 molar at 20 seconds to 0.230 at 30 seconds. You take the difference, comes out to 0.086. So this is the change in concentration of A in the third 10-second range. Because if you remember, we did 0 to 10, 10 to 20, and now 20 to 30. And the change in concentration, let's see, we found that it was 0.164 in the first 10 seconds. It was 0.120 in the second 10 seconds, and now it's only 0.086. So what you can see is that the reaction is certainly slowing down, as we expected. All right, so putting that together, let's see, at 10 seconds, so initially the concentration was 0.6 molar. After 10 seconds, the concentration was 0.436 molar. After 20 seconds, it was 0.316 molar. And after 30 seconds, 0.230 molar. So I'm going to talk a little bit about something called the half-life. And what this D asks you to do is estimate the half-life. Now, what is the half-life? The half-life is the time it takes for the concentration of the reactant to decay, in other words, to go down, decrease, to half of its initial value. So we started at 0.6. The half-life, which we often call T1 half, would be the time it takes for the concentration to get to 0.3. Okay, so you notice here that, let's get these colors back, that 0.3 is somewhere between 0.23 and 0.316, closer to the 20 seconds. So I would say that it takes a little more than 20 seconds to get from 0.6 to 0.3. Okay, so I would estimate that the half-life is a little greater, a bit larger than 20 seconds. Okay. All right, so now I'm gonna skip a little bit. I'm gonna talk about some other stuff related to this, and then I'll come back to what the half-life actually is. So what I'm going to do is take a closer look. So it's time for a closer look at this equation. The equation that we've been working on for a while. So if we were able to take data for how the concentration changes during a chemical reaction, and if that reaction was first order, so that if we were able to take data for how concentration changes over time for a first order reaction, because remember, this equation is only valid for a first order reaction. So if we were able to take data, suppose we had data for how the concentration changes over time for a first order reaction. And how would we get this data? So one way we could get it is a lot of times we could use the fact that concentration and absorbance are proportional to each other. So we could, for example, monitor the absorbance with time. And in fact, I showed you data for this on the very first day we studied this when we were talking about the crystal violet reaction. that if I took a sample of that crystal violet as that purple color was fading, okay, over time, the color fades. And as the color fades, the chemical that's doing the absorbing is actually decreasing in concentration. And so it would absorb less and less as it had a smaller and smaller concentration. So one way I could get data for how concentration changes over time is I could look at how absorbance changes over time. And if the reaction was first order, it would have to obey this equation. The log of the concentration, let's say, of A, the reactant, is the log of A0 minus KT. So if this is the equation that represents how the concentration changes over time, then it tells us what we can do to actually figure out if the reaction is first order. Like, suppose we didn't know the reaction was first order. How could we figure out if the reaction really is first order? So how could we figure out if the reaction is first order? I don't know what's going on here. I probably have too many windows open or something. Okay, and what we could do is if you take a close look at this equation, you see now, and let's not forget that what we will have is we will have data for the concentration of A versus T. So we'll have this concentration of A and time. So we'll have all kinds of numbers here. Okay, and if we did a graph of the concentration of A versus time, we know that graph would not be a line. This would not be linear. But if we take a close look, as I've been promising for a while now, at this equation, if you actually graphed, instead of the concentration of A, the natural log of A versus time, okay? So if you put this on the y-axis, so you put this on the y-axis, and put time on the x-axis, we see that there is this linear relationship between the log of A and time, okay? Because the log of A0 is just a constant. It's just the log of the initial concentration. Like in the example we spent a long time on, this would be the log of 0.6. That's just a number, right? That's minus 0.511. That is not changing. So that's a constant. And also, of course, the rate constant is a constant as long as we don't change the temperature, okay? So if we graphed the log of A versus T, well, we would see a line, and the line would look like that. And from this equation, you could see the log of A is the log of A0 minus KT, that the slope, okay, so if this is what's plotted on the x-axis, and this is what's plotted on the y-axis, then the slope is minus k, because remember we have y equals b plus mx, and so that slope is the negative of the rate constant, and the intercept is the natural log of the initial concentration. So this guy here is actually the log of A0. So that's the maximum value that the log of A will have, is its initial value when A is at its maximum concentration. And then over time, this will go down in a linear fashion. And the slope is minus k. Okay, so the greater the rate constant, the steeper this slope is going to be. This is what's going to happen if k is greater. You know, it would be steeper for a larger k. So you would have a much more precipitous drop in the concentration of A, or the log of the concentration over time. So what's the big conclusion here? Okay, so the big conclusion is that if we plot the log of the concentration of a reactant over time, and we get a linear plot, then it means the reaction was first order. So we have a method of figuring out if that reaction is first order. Now, this is not the only method that we know to figure out if a reaction is first order, because what else could we do? How could you figure out if a reaction is first order? So there's another way that we learned, right? We learned that if you say double the concentration and the reaction is first order, that will double the rate. If you double the concentration of a reactant and the rate, quadruples, then the reaction is second order. So one way to determine if a reaction is first order is to double the concentration of that reactant, leaving anything else constant, and seeing what happens to the rate. And if it doubles, then the reaction is first order. So the other way is to say double the initial rate, the initial concentration. You can't double the rate, you have to double the concentration of reactant. If the rate, which we usually measure the initial rate, doubles, that means the reaction is first order. So that's one way to get to figure out if a reaction is first order. So that's one way. The other way is you plot the log of that concentration versus time. If you have a linear graph, it means the reaction is first order. And you also get the added bonus that the rate constant is the negative of the slope. So that's a very nice thing to know, to be able to use. So let me talk a little bit about half-life, because I gave you a little introduction to what it means, but we can actually use the equation that we know for first order reactions to figure out the half-life. So we're going to get a formula for it, for a first order reaction. Okay, so remember what the half-life is. This is the time it takes for the concentration of a reactant to decrease. The half-life is the time it takes for a reactant's concentration to decrease to half of its initial value. Okay, so I'm going to work on the half-life formula for a first-order reaction. But first of all, I want to review a little bit that if you plotted the concentration for time versus time for a first-order reaction, it would definitely not be linear. Remember, it's linear if you plot the log of A versus time. So, but I want to show you on this graph what's meant by half-life. So let's suppose you start at the initial concentration A0, okay, A being the reactant. So we're talking about A goes to products, and the rate is K times the concentration of A. And the concentration, of course, is going to decrease with time. So here is what it is initially. Okay, so this is the concentration over time. And when it gets down to half, so this is it's about half of is about here. So this, the time it takes for the concentration, so let's say we started with this concentration, and this is about half of it. Well, it's not a very good drawing, but you'll have to imagine with me. So this is half the half-life that has elapsed. That's what this would be. It would be T1/2. Now, then we have this concentration. Okay, now if we go down to half of that, that's another half-life that has elapsed. So this would actually be 2t1 half from the 0. Okay, so every time a half-life passes, you get half, you're down to half the concentration of what you started with. Okay, so so we're going to come up with a formula for that half-life. Now this behavior where where every half-life it drops to half of what the concentration was before. So we're going to analyze this only for a first order reaction, okay? And so no matter where you are in a first order reaction, the half-life later, so the number of seconds that equals a half-life, if you wait that long, you will have half of what you started with, no matter where you start, okay? We'll talk about that more as we go along. So in order to get a formula for the half-life, we start out with this equation that we've used before, which, like I said, is only for first order reactions. Okay, and so what I'm going to do is subtract the log of A0 from both sides of this equation. So on the left now, I'll have the log of the concentration minus the log of the initial concentration equaling, these are going to cancel, minus KT. So then I'll use the rule of logs, all right? So the log of A minus the log of B is the log of A over B, okay? So this becomes a log of A over A0 is minus KT. And you could leave it like that, or you could realize that, it's another thing with logs, that if you reverse the order in here and make it A0 over A, then you would change the sign. So these equations, both of them, are usable as a starting point for figuring out the half-life. We haven't gotten to that formula yet, so I have to move this equation, this section down a little bit. This, of course, it's not doing it because that's what it does. Ah! I'll try it one more time and see if I can do it. Oh, look at that, it worked. Let me get some more room in here. I feel just as silly doing this as I do in class when it doesn't work. But okay. So so if we have this log of A over A0 is minus KT. And now I say at the half-life. So what does that mean? At the half-life. So in other words, after a time T1 half has passed. Okay. What is the concentration? Well, it's equal to 1/2 of the initial concentration. Okay, so it's A0 over 2 or 1/2 A0. So at the half-life, T equals T1/2, whatever that is. And the concentration of A is the initial concentration over 2 or 1/2 A0. So, so that means that A over A0 at the half-life would be 1/2 A0 over A0, right? Because at T1/2, so when T is equal to T1/2, when T is equal to T1/2, A is equal to 1/2 A0. So at T1/2, this ratio here becomes 1/2 A0 over A0. So we know that the log of that is minus k, but I'm not going to put t in here because I know that the time when this occurs, when this when a is 1/2 a0, so in other words, when I can substitute 1/2 a0 for a, okay, that I know that that happens only at the half-life. So I end up with this equation here, and this is the log of this whole thing, but you could see I have a0 in the numerator and the denominator, so I end up with the natural log of 1/2 is minus k times t 1/2. And here's another little clever thing about logs, okay? The natural log of 1/2 is the negative of the natural log of 2. So that's equal to minus k t 1/2, and now I can cancel. Believe me, you don't have to know how these things are derived. You just need to be able to use the formula. Did I do that right? What is the log of 2? I need my calculator. I think it's right. Yeah. So the log of 2 is actually 0.693, and that equals k t 1/2. So all of that messiness, which you can just forget now because you don't need to know it, boils down to this one formula. This is the half-life formula. Okay. So we have this formula, the half-life formula, which you could write in either of these two different ways that I point out here. And so we need to calculate the half-life for this reaction. So we're going to use that formula. T 1/2 is 0.693 over the k. And remembering this is activity 6 that we started on a while back, and the k is 0.0320 inverse seconds. So just take 0.693 divided by, notice the units are going to be the reciprocal of inverse seconds, or seconds, which is very nice because that makes sense. Okay, so the half-life is 21.7 seconds. Now it says, how long would it take for the concentration of A to decrease from 0.6 to 0.075 molar? And it says to figure out how many half-lives this is. So what you need to remember is every time the concentration decreases by half, it means a half-life has passed. So in 21.7 seconds, it'll go from 0.6 to 0.3 molar. Another half-life, or 21.7 more seconds pass, it'll go down to half of 0.3, which is 0.15. And then in another half-life, another 21.7 seconds more, it'll go down to half of this, which is 0.075 molar. And that's what we want. So basically, the answer is 3 half-lives to get from 0.6 to 0.075 molar. Now, the numbers don't always work out so nice, okay? But you can always solve the problem a different way. By the way, let's multiply this by 6 to finish the problem, and you get 65.1 seconds. So you could also do this problem using the formula, this equation that I derived for you a little bit earlier. I'm going to use this one here. Let me recopy it. What's going on? It's kind of slow, kind of delayed. Okay, so the log of A would be, well, the A here would be 0.075. A0 would be 0.6. So the log of 0.075 over 0.6 is minus kt. So let's calculate what this is first. 0.075 divided by 0.6 is 0.125. So the log of 0.125, which is negative 2.0794. I'm keeping a lot of figures. I don't want round off error. Is minus kt. So we know what k is. I'm going to divide both sides by minus k. So then the t will be, well, let's get rid of the negative signs. You can cancel them. All right, so if you do the math here, guess what? You get 65 seconds, which is almost the same. You know, you should get exactly the same answer. Well, these are close enough. So if you have numbers that don't work out, like let's suppose you can't just divide the initial number by half and by half and by half. Like let's suppose I asked you, well, how long will it take for the concentration to be 0.09? Well, you're not going to get there by half-lives, so you can always solve the problem this way, using this formula here. Okay, so here it says, if you know the concentration of A at 10 seconds is 0.436 molar, we did that earlier, what is the concentration of A 21.7 seconds after that? Well, you have to recognize that since we just calculated it, the half-life is 21.7. So 21.7 seconds after it's 0.436, it's going to be 0.436 divided by 2, or 0.218 molar, okay? Because a half-life has passed, 0.436 in a time t1/2, or 21.7 seconds, it'll go to 0.436 over 2, or 0.218, okay? So here's another problem. It's a reaction of this cyclical carbon, this 3-carbon cyclical compound. Carbons are bonded together in a ring. And so you go from cyclopropane to propene. There's a double bond there. That's why this is propene and not propane, which you'll learn more about when you take organic chemistry. So here is the first order rate law. The only time we can figure out what concentration is as a function of time is for first order, so it has to be first order. And this problem here I'm not going to do right now, because this is just like what we did in activity 6, where you have an initial concentration and what is the concentration after a certain time passes. We did lots of problems like that. So instead, I'm going to go on to part B. So here's a problem like the one we just did. If the initial concentration is 6 molar, at what time, so we're trying to figure out what the time is, will it become 0.15 molar? And here, we're using the equation that I used before, except we're putting in a C for A, since C is the reactant. Okay, so what I'll do is plug in these numbers, the log of 6, well, I don't need to put brackets, it's just over 0.15 equals minus kt. So let's first figure out what this is. That's the log of 40, natural log, 3.689. Then I'm going to divide both sides. You see, we're given k. Okay. I'm going to divide both sides by minus k. So we cancel these out. So the time will be 3.689. Oh yeah, I reversed these numbers. So this comes out to the log of 1/40th instead, a log of 0.025, which is negative 3.689. So I could tell I was getting the wrong answer because I would have had a negative time, and that just doesn't make sense. So I have to divide by k. 3.689 divided by, it comes out to 0.401. Okay, so that's how you do that sort of problem. And then what is the half-life of this reaction? Oh, the reaction takes place at 1,000, so that's not really relevant to the question. So the T1 half is 0.693 over K. And that comes out to 0.0753 seconds. Not very fast, not very long at all. So it's got a faster rate constant in this problem than the rate constant we used that was 0.032, and so we have a much shorter half-life. And then finally, part D, if the initial concentration is 10 molar, when will the concentration fall to 1.25? And here is a case where you can have everything. So what I'm doing here is I divide this by 2, then I divide it by 2 again. And each time, the time that elapses is a half-life. And so sometimes when the numbers work out, this is pretty easy, and you end up with 3 half-lives. And since the half-life is 0.0753, this comes out to 0.225 seconds. Okay, so that's pretty fast.